Welcome all. We will continue our discussion on unsupervised learning. Last class we began with our discussion on what unsupervised learning is and defined unsupervised learning in terms of latent variable models. That is what we had done. So, we will continue our discussions there. So, recall that in unsupervised learning we are given data which is a set of in realizations from a particular random variable. So, here note that the difference between this and the supervised learning is that you do not have the label random variable, you only have the data or features random variable that we have observations from. Now, the goal of unsupervised learning is still estimating the underlying distributions. The goal here is still estimate given D, which is still the same problem that we have, and we use the exact same techniques that we have seen in this course, which is minimizing the KL divergence or divergence metric. But the distribution that we will be looking at right now is the marginal of and you can see if there is Py, then this can be called as a marginal distribution, otherwise it is some distribution that we would want to estimate, underlying distribution that we would want to estimate. So, also told you that one of the most famous ways of doing it is to model Px via a latent variable distribution. That is, you call P theta as the marginal over the joint distribution of x and z, where z is a latent variable. Now, procedurally you solve the exact same problem of divergence minimization and estimate P theta. Once you have a latent variable model, as a byproduct of having a latent variable model, we also get distributions such as P theta of z given x, which is the conditional of the latent variable given data, right, and that can be used for several purposes. So, now the question is, what is the use case or application of estimating an underlying distribution given D? See, in the case where we had another random variable which we called label, the use case was pretty obvious that we want to estimate the posterior of label given data, and that we called as classifier or regressor. So, given a new data point, you pass that new data point through this estimator and get an estimate of P of y given x, that gives you a distribution over labels. Now, in the unsupervised learning case, why do we need to estimate the marginal is the question. So, why do we need P theta of x to be estimated? So, as I said, in the latent variable modeling scheme, once P theta of x is estimated, so one can estimate P theta of z given x, which is the posterior of the latent variable given data. Okay. So, now this can be looked into as clustering the data space x if z is discrete, and this is feature extraction or embedding or feature extraction if z is continuous. Yeah, if we estimate the underlying distribution well, then the posterior of the latent variable given data can be looked into as a way to cluster the data if z is discrete, and if z is continuous, then it can be looked into as some representation or feature extraction that you are doing from the data space. I told you in the last class, right, why can you look into this as clustering is suppose Z is discrete and you are looking at k short discrete random variable, then P of Z given x will tell you whether this x belong to one of those k possibilities of Z. So, that is grouping of data, which is also called clustering, right. So, any unsupervised learning algorithm that has a latent variable formulation with Z being discrete can be called as a clustering algorithm always, right. And any unsupervised learning algorithm which has a latent variable formulation with Z being continuous can be seen as a feature extractor or an embedding extractor. So, that is the way to look at it. Okay. So, now with this prelude, let us look at a few algorithmic ways of doing this. We already saw how to estimate latent variable models, right. One latent variable model that we saw was the Gaussian mixture model, which was estimated, whose parameters were estimated using the EM algorithm, which is still maximum likelihood estimation, but we need to look at the EM algorithm to do that. So, let us start from that. So, case 1, here Z is discrete and we have x to be in RD. In this case, what do? We write P theta of x to be equal to sum of P theta of Z times P theta of x given Z. This is the definition of the latent variable model. So, in a mixture density, we make this to be a discrete random variable and call the density represent the density P theta of Z with alpha m, and all these individual component densities are Gaussian distributions with a particular mean and a variance mu or sigma. Yeah, this is our GMM model. So, you remember this, right. Now, there are m components here. You can write this to be capital 1 to m. We have this discrete random variable Z now can take one out of capital M values with probabilities alpha 1 to alpha m. So, that is the model, right. Now, estimate alpha star, estimate theta star, which is the set of alpha stars, and we have mu stars and there are sigma stars via EM. So, I will not expand this because we know how to do this, right. Given a particular data set, we know how to get the parameters of an underlying GMM using EM algorithm. So, we assume that we know this. We estimated these parameters now. So, once we estimate these parameters, how do we use this is the question, right. So, having estimated theta star, given a test data point, it does not have to be a test data point actually, given a data point x from the distribution, it can be from D or it can be outside of it as well. So, let us generalize this, x sampled from the underlying distribution Px, we estimate, rather calculate, because estimation is done, P theta star C given x. So, what is this equal to? Is equal to P theta star x given Z times P theta star Z divided by the sum of that P theta star, call it as x because there is a sum over that. Okay. We know how to estimate all of these terms. The RHS is completely known post estimation. So, we can get P theta star of z given x. Now, what is this? This is a distribution over z given x. So, given a data point x, so this gives you an entire distribution over z, correct? That is what it is giving. So, how does that look like? For every x that is sampled from the distribution Px, say distribution over z given x will look like this. So, this is P theta star z given x, this is z, and we will have right. So, this is 1 to capital M. So, for every data point we get an entire distribution over z, correct. This is what we get once we calculate P theta of z given x, P theta star of z given x, right. So, what is this? This is it represents soft clustering, as it is called. In the sense that it is saying that with probability this much, it belongs to the fourth group. See, basically the idea is the following. If you recall what a mixture density is, we are modeling every point as a linear combination of multiple constituent densities. Okay. Now, what is this saying? What is P theta of z given x is saying? That with what likelihood that this data point x belongs to that particular component in the mixture, isn't it? So, P theta z given x is given x, what is the likelihood that this particular x is belonging to this particular component in the mixture density. Okay. If you look at each of the Gaussian components in the mixture density as a group, okay, within the data space, that is exactly what is being done, right. If you have the data space and if you have k Gaussian densities that you are trying to model the data space with, each of the Gaussian distribution is partitioning the data space into groups. But when I say Gaussian density is partitioning the data space, it's not very intuitive, because all Gaussian densities have infinite support. So, all of the Gaussian densities would overlap, isn't it? The support of all of these Gaussian densities would overlap, but depending upon where the mu stars and sigma stars are, so the spread that each of these Gaussian densities will have will be different. Okay. Now, if you look at each of the constituent densities in a mixture model as grouping of data, given a data point, P theta of z given x is telling you with what likelihood that this data point belong to that particular component in the mixture density. So, that way this entire P theta of z given x can be looked into as a way of clustering data, right, albeit soft. What do you mean by soft? There is a non-zero probability of this data point belonging to all of the constituent groups. What is it a consequence of? It is a consequence of the fact that the constituent densities are Gaussians that have infinite support. Does it make sense? Okay. So, this is called GMM clustering. So, this entire thing that we just saw is called GMM based clustering. So, now if you look into this entire thing as a black box, so given a data set, what you give is for every data set, you give a vector of dimensions m, which is P theta star of z given x. That is called GMM clustering. Okay. So, what do you do with this information? Okay, you cluster data. What do you do? As I said, you can use this distribution itself as a feature and then solve a downstream task. When I say downstream task, it means that let us say that you have labels associated with it. You first cluster it without labels and get your z's, and use those z's as data, associate labels that you already have, and solve, use another neural network or something to solve your classification or regression task. That is how you can do that. Or once you cluster it, you can visualize them, right, and also see you will get information about, okay, See, what happens is typically when you are given data and if you do not have labels, suppose you run a clustering algorithm like GMM, what is it actually telling you is that it is roughly telling you how many, what is the likelihood that this entire data gets grouped into 10 different classes. You should not call them classes. I hesitated a little because they are not classes, they are simply subsets of support. That is it. I mean, the entire ambient space of data, what are the groups that you can look at. This is also called exploratory data analysis, because what you are trying to do is you are trying to explore how data is grouped or clustered. Make sense, right? In fact, the hyperparameter here is this capital M, the number of clusters that we would want. And whenever you run a GMM algorithm or a clustering algorithm in standard packages, you will have to choose M as a hyperparameter. How many groups do you want? Okay, so this is GMM clustering. Now suppose we want to turn this soft clustering into hard clustering, in the sense that, so let us write it down. Suppose we want P theta star of z given x to be Dirac deltas. So, we will understand what Dirac deltas is, right. With probability 1, it should belong to one particular, it should take one particular value and it should be 0 everywhere. Now, how do we change GMM so that the posterior of the latent variable given data becomes Dirac delta? Any okay, I mean, of course you can take maximum out of it, that is a post facto thingy, right. But can we put some constraints on the way our component mixtures are, so that by construction P theta of z given x becomes Dirac delta is the question. We can
make it fixed support.
Correct. So that is the way to think about it. So now we should make it fixed support, meaning all these Gaussians that we are looking at have to have fixed support. In fact, it does not suffice if you have fixed support, it should have infinitesimally small variance, right. Only then it will partition the data space into non-overlapping subspaces. You understand what I mean? So, in this case what should happen is the constituent Gaussians should have, all of these should have different means, but variances which are diagonal, okay, and we want this variance to go to 0. We need to have infinitesimally small variance. Okay. So, if you do this, what will happen is this implies with this these becomes, all of these posterior will become Dirac delta. So, what does that mean? For a given data point with probability 1, a given data point with probability 1 belongs to only one cluster, that is it, one of the constituent Gaussians, not all of them. Okay. Now, the interesting part is, suppose we make this change, okay, which is this, the EM algorithm that we know of will take a surprisingly simple form. Recall what did we do in the EM algorithm. So, we had two steps. What was the first step? Of course, we have to find that expectation of the joint distribution. Now, recall what the elbow is. Sorry, not elbow, the EM algorithm. So, what was that? The E step. So, you compute the expectation of, I think this joint distribution, right. Can somebody remind? It was the, was there a log here? think it is p theta of the joint distribution of this divided by qz, actually z given x, right, that is what we were saying, and this expectation was with respect to q z given x. In fact, I mean this is what we did, but if you recall, I can actually effectively take this denominator out, because the it will be the entropy and it is independent of whatever we do, right. I can actually take this out, remember, right. So, this is the E step, and what is the M step? So, we had to do the argmax of the optimization is over the parameter space, and what is the objective function here? This thing, right. So, these are the EM step that we do. Now, suppose you assume the constituent Gaussians to be of this form, they have different means and their variances are infinitesimally small. Okay. One can mathematically show that these two steps, okay, will converge into something that I will just then mention. So, you have to take that as a homework and show that exactly they are the same. But what will happen is the following. Okay. So, the E step, okay, let me first write down that algorithm, which is actually called the K means clustering algorithm. Let us call this M means clustering, because we are saying that there are M components. Initialize M mean vectors randomly. Okay. So, while convergence do. And by the way, what is the optimal q z given x in EM? Actually, the E step also has one other thing, right. So, you have to set q of z given x to be p theta of z given x, right. This is there, we also have this, right. Okay. While convergence do, what do we do? First, assign xi or every xi each xi to one of the M means via solving this. So, you take argmin it does not matter, no, because it's just a distribution over z. It can be the conditional or can be marginal as well. Yeah. So, what you have to do is that you assign each of the data points xi, okay, by minimizing the distance between that data point and all the means that we have. So, while convergence we will have to do this, we will have to assign each xi to one of the M means by solving this optimization problem. Now, what are we doing? There are M mean vectors. Calculate the distance of the point under consideration, the data point under consideration from all these M means, okay, and look at the one that is the closest, okay, and you assign this data point to that particular mean. Do you see this? This is the first thing. So, what do we have right now after the first step? Every data point in the data set is assigned to one of the means. Okay. The second step, what you do is recalculate mu m after the assignment. . as, so mu j is equal to 1 by the cardinality of set j sum over set Sj and all xj's that would belong to this set j where Sj is the set of all data points that got assigned to mu j in step 1. Do you see this? Start with random initialization. In the first step, assign each of the data point to one of those m means by looking at what is the closest to that data point, and once you have it, you have one assignment, right. Now update the assignment by taking the mean over all those data points that are assigned to a particular mean.
So it will be slightly shifted.
It will be shifted, right, because initially you started randomly, then you assigned based on distance. Once the assignment is there, you compute the mean again. So new means will emerge, okay, and keep doing this.
What if your data point is equidistant?
Break the tie arbitrarily. That is how it is done. The ties are broken arbitrarily. So this is end while. Upon convergence, end while. Upon convergence. Now, what is the convergence criteria? Is that put a bound on how much the mean is changing at every step, right. If choose an epsilon, if the mean assignments is not changing more than epsilon, okay, in magnitude, then stop there, okay. So this is called the k means clustering algorithm, m means or k means clustering algorithm. So it takes k as an input and divides data into m distinct clusters. So now once this algorithm is done, what have you actually done is that every data point is assigned to one of the m clusters. Now my claim is that these two steps are exactly the expectation and the maximization steps. Okay, can somebody tell me where is the expectation and where is the maximization happening? Step 2 is expectation, step 1 is maximization, right. Assignment is maximization, because why? Getting a starting with what is starting with p theta of z given x. So p theta of x z given x is one cluster assignment, because now z is discrete and we are looking at Dirac deltas. All p theta of z given x is now Dirac deltas, right. Once you assign each of the data point to a particular cluster center, this is what we are doing. Once we do that, we compute these expectations, and this expectation is nothing but getting the new cluster centers, which is getting a new estimate of this, and then you assign based on maximizing this particular thing or minimizing the distance. How did this maximization turn into the minimum distance? It's because there's a Gaussian and we have e power minus term in the exponentiation, and that minus will just make this maximization into a minimization thing. So here is a homework. So show that the GMM algorithm that is applied with a constraint that our Gaussians are having this particular form with the variance going to 0 will give rise to this k-means clustering algorithm. It's pretty simple to show actually, right? And if you do the math, it will just nicely come out. Okay, so this is the hard clustering algorithm. All right. Any questions here?
Do we have convergence guarantees or any proof like perception?
So this is EM. So since this is EM and we know what EM does, all that we have is likelihood does not decrease. that is it. K-means clustering algorithm is nothing but EM. So, it is as good as EM. Okay. In fact, you can kernelize this as well. What do you mean by this? Instead of operating on the data space X, you can operate on some transformed space phi. Okay. And again, this is another nice little homework to do, that you should show that if you take a transformed space phi, then the K-means clustering algorithm does not require you to actually compute the transformation as long as you have the kernel, just like we did with the kernel machines, right. So, that is called kernelized K-means. Okay, you can do that with using a kernelized space as well. Okay, so this is about the clustering algorithms, where we explicitly model the data using a latent variable model and try to find the distribution p theta of z given x. Okay. Now, there are algorithms where the model is not explicitly made to be a latent variable model, but you make it an implicit latent variable model. We will take some examples on that. Okay. In fact, so what do I mean by implicit latent variable models? Suppose you build a neural network on some data. Now, remember I told you that a neural network is a composition of linear and nonlinear function, it is a composite function. You can break the composition at any time and call that as an embedding or a representation. So, what do I mean by that? Suppose you have an MLP which has 10 layers. If you tap at the 5th layer of an MLP, that is still a transformation of data, you can still treat that as an implicit latent variable model. Do you see that? So, now the only thing is that actually I mentioned this during transfer learning as well, right. So, you train a neural network and then tap the features at an intermediate layer and use it for downstream tasks. But typically when you use a neural network as an implicit latent variable model, you would not solve the implicit latent variable model on a classification task. What do I mean by this? You do not want your neural network to be trained for estimating the conditionals given a particular type of label set. Why is this? Think about it. Let us say that I have images of digits, handwritten digits, which I am talking about the MNIST data set, right. Now, suppose I build a neural network to solve the problem of classifying digits from 1 to 0 or whatever, right, 1 to 10. Then that neural network has partitioned the data space into the semantics as imposed by this particular labeling scheme. Let me repeat, this is something which is important to understand. Every classifier can be seen as a method to partition the data space, that we have seen, right, during the discussion on decision trees and all that. Given a classifier, what does it do? It will partition the data space into non-overlapping subsets, or rather overlapping or non-overlapping subsets. Now, given a labeling, what does this partition depend on? This partition depends on the labeling scheme, right. So, now if I have built a neural network to solve one particular problem of discrimination, which is a particular estimating a particular posterior density of the labels, then I have partitioned the data space in one particular manner. Okay. Now, suppose I take features of such a neural network, these features are highly correlated with that particular label set. Now, if I have given a neural network that is trained on MNIST with the task of classifying digits, I cannot use those features to classify that same data set on, let us say, the orientation of digits. Suppose I want to solve another task where I would say that every digit or every picture that has a knot like 3, 5, 8 and all that, right, or curves for instance, have to be in one category. All the images that does not have a curve should have to be in some other category. It turns out that the features that I have extracted, okay, from an implicit latent variable model, which is a neural network, by solving a task that would differentiate digits, digital semantics, cannot be used for this task, because the partition that this particular neural network has learned is not correlated with some other task, but it is correlated with that particular semantics that we have imposed on data space. Does it make sense? That is why when solving, when extracting latent variables, you try to estimate the marginals but not the posterior on a particular given semantic, which is called the labels. So, that is why people estimate the marginals, not the, or rather estimate get the features by solving marginals or by estimating the marginal densities, but not the posterior with a particular semantic. Do you understand what I am saying, right? So, now what we will see is how do we use the neural networks and the other kinds of linear models to get the features or implicit latent variable models solving tasks which are not conditioned on a particular label semantics. Okay. I will give you a few examples of such tasks and then we can close this. We will stop here and continue in the next lecture.